Questions? All right, today we're going to just continue with reactions. So we're interested in the chemical properties of reactions. So let me just skip this stuff here. Normally when we look at the classification of chemical reactions, there are a whole bunch of subcategories here. For example, combination, decomposition, acid-base, single replacement, double replacement, combustion, and so forth. What we're going to do with this this list, and if you look at the Chem 4 supplement, like a dozen different types of reactions to memorize. The list is a bit too long. Not only that, it's not comprehensive. It's okay if it's a long list, if it's comprehensive, but we'll have reactions like this. HCl, HNO3, and AU together. And this doesn't fit one of those categories that I just listed, nor does it fit any of the categories in the supplement. And so we need a broader chemical reaction scheme. Not only that, the category of reactions earlier would classify these two reactions in the same category. These two reactions would be a combination type reaction where you take compound A or substance A, substance B to get AD. In this case, these would be the elements here as compounds. But those two reactions are quite different in terms of what we're looking at. And so I have this alternate classification scheme I like to use, and I like to subdivide the chemical reactions into three types. One, metathesis, two, acid-base, and three, oxidation reduction or redox reactions. So three types of reactions, three basic types of reactions. We looked at metathesis reactions in lab on Thursday, and so let's just talk about metathesis reactions today. But whenever we have a reaction, the reactions, there's got to be something driving the reaction. And what's driving the reaction is a driving force. And so the three basic types of reactions are based on driving force. Metathesis has a certain driving force, acid-base, and redox have certain driving force associated with them. And what is a driving force? A driving force is just going from less stable products to more stable, less stable reactants, all right? We want to formation of more thermodynamically stable. Now, thermodynamically is just energetics. Something's high energy, it's thermodynamically unstable, lower energy, it's thermodynamically stable. So we want to form more stable products from less stable reactants. And so there's certain things that we look for. The certain things that we look for are let's see. Let me jump ahead here. Certain things we look for are like the precipitates. We'll precipitate form, which is a insoluble solid. Also, gas formation, or stronger acid to weaker acid. These are the types of things we look for in metathesis. And that would be finding favorable ion combinations. Favorable ion combinations would be, the ions like to, in other words, bond with each other. And so probably the easiest way to learn this stuff is just to go through a lot of examples. Okay, when we look at metathesis are ion combination reactions, but some things, like ammonia, also react in metathesis reactions. And these are called weak electrolytes here. Electrolytes are salts. Salts create ions in water. So weak electrolyte, molecular compounds might participate like ammonia. Ammonia doesn't contain any ions, but ammonia can react with water to form ions. So that's why we might consider ammonia in metathesis reactions. So let's look at just examples of this. But when we look at examples, we have to look at what ions like each other. And what ions like each other are ions that will combine to form insoluble precipitates. And so in order to determine what insoluble solids exist, we need the solubility rules. So let's just review the solubility rules quickly. We'll start off with the first rule here. Group 1 and ammonium compounds are all soluble. Okay, then 2, what do we do next? Look at the anion. If the anion is, what anions do we consider first? Acetates, chlorates, nitrates. Sulfates are in a different category. Acetates, chlorates, and nitrates are all soluble. And then after that, we look at chlorides, bromides, and iodides are all soluble except silver, mercury 1, and lead 2. If it's not chloride, bromide, or iodide, we look at sulfates. Sulfates are all soluble except for silver,
mercury 1.
Yeah, we do silver, lead, mercury, calcium, strontium, and barium. Okay, those. If it's not any of those, then we look at hydroxides. Hydroxides, however, are mostly insoluble. So hydroxides are insoluble except for group 1, NH4, calcium. Yeah, okay. We'll go in the order of the list here. Calcium, strontium, and barium. And then if it's not a hydroxide, we look at sulfides. Sulfides are all insoluble except for group 1, ammonium, and group 2. And then if it's not a sulfide, we look at carbonates, phosphates, and chromates, which are all insoluble except for group 1 and ammonium. And so that takes care of the solubility rules. And so if we form a precipitate, precipitates are stable, strongly bonded, and so that's what we call a driving force, a more stable product. Another more stable product are the weaker acids. Weaker acids are more stable, less reactive than stronger acids. And so if we go from a stronger acid to a weaker acid, then we're okay. For Chem 4, we're going to have to memorize some acids. Acids usually start with an H, that's their cation. We have these acids are called the strong acids, perchloric, hydroiodic, etc. The strong acids, there's 7 of them, and most people just memorize them. These are the 7 common strong acids. There are other strong acids that aren't on this list, but they aren't that common. And so people typically memorize these. And then if it's not one of these, then most likely it's weak. And so if we do the 7 common strong acids, we have perchloric, hydroiodic, hydrobromic, hydrochloric, this one, HClO3, chloric acid, H2SO4, sulfuric, HNO3, nitric. So those are the 7. So if we had something like phosphoric acid is not one of the 7 we memorize, therefore we assume it's weaker, a weak acid, what we call weak acid. These are all weak acids. The weak acids, though, will have varying degrees of strength. Phosphoric is one of the stronger weak acids. This one, trichloroacetic. Trichloroacetic, notice it doesn't begin with an H. This formula that's written here is called a condensed structural formula. So it shows how the molecule is put together structurally. And you can go down the list. Water is way down here. Do you see it? Water is quite a weak acid, and these are acids that are even weaker than water. Normally when we think about water, we don't really think of it as being very acidic, do we? We think of it as being more neutral. All right, so this is on the handout here. Then we also look at a gas formation, like for example, hydrogen ions like carbonate ions. When hydrogen ions and carbonate ions combine, it forms this, which is called carbonic acid. However, carbonic acid, is it stable? No, carbonic acid is not stable. What does carbonic acid decompose into? And so as far as metathesis goes, that's a favorable ion combination. So if we had two hydrogen ions and a carbonate ion, we're going to form H2CO3. But H2CO3 is unstable, and H2CO3 will decompose into H2O liquid and CO2 gas. And so this is a reaction that we saw in the lab on Thursday. Hydrogen ions and carbonate ions will effervesce the formation of CO2. There are other species similar to carbonic acid. One is sulfurous acid. Sulfurous acid is unstable as well. Sulfurous acid is going to form H2O plus SO2, sulfur dioxide. So rather than carbon dioxide, we form sulfur dioxide. This is also toxic. This is ammonium hydroxide. Ammonium hydroxide is unstable. It's unstable, but a little bit it can form. Actually, a lot of these reactions are thought of as like two-way reactions. And so ammonia can participate in metathesis because ammonia reacts with a little bit of water to form a little bit of ammonium ions and hydroxide ions. But this is an unstable combination. This is why it's much more favored in the reverse than in the forward. So I drew uneven arrows in class on Thursday just to show that just a little bit of this forms. A little. We can't have too much of this form because what will happen is the ammonium will react with the hydroxide to decompose. Do you know what ammonium hydroxide decomposes into? Ammonium hydroxide decomposes into ammonia and water. So this reverse reaction is favored. And so it depends on the downhill direction, what we see. As we want to go lower in energy. And so if we go this way, it's uphill because ammonium and hydroxide are less stable than ammonia and water, so it's uphill. But it's not too severe, If some things are steeply uphill, then nothing makes it to the top of the hill. But if it's not too steep, then a little bit can make it. Not everything, but a little bit can make it. That's because, when we look at the energy, like for example, this water is at room temperature. Does that mean that every water molecule in this container is moving with the same kinetic energy? That's the same motion? Like they're all water molecules, and this water sample is at room temperature. Does that mean all the water molecules are moving at the same? No. The water molecules don't. There are going to be some water molecules that move a lot faster, some that move slower. The same thing with ammonia. And so if we have a violent collision, it can make it up this hill to form this. But normally to go downhill, it's the opposite way. These are less stable here. These are more stable, so it's downhill going backwards here. Some things like, this, they don't rely on decomposition. So for example, hydrogen ions like sulfate ions. In fact, we'll need two hydrogen ions, and this will form H2S. H2S gas, which is toxic. Same thing, hydrogen ions like cyanide ions. That's going to form hydrogen cyanide gas, which is extremely toxic. So there are other examples of gas formers as well. So metathesis deals with ions. So when we're dealing with ionic compounds, then it's a metathesis type reaction. And so what is the formula for calcium carbonate? CaCO3. Are carbonates, well, let's go on. Sulfuric acid, what's the formula? H2SO4. Sulfuric acid, this is not pure sulfuric acid, because sulfuric acid is a mixture of H2SO4 and water. It's an acid mixture, the acid and water. And so if we were to look at this, there's water present. There's water present, will the calcium carbonate dissolve? Do carbonates dissolve in water? Well, it depends. Carbonates, phosphates, and chromates are all insoluble, except group 1 and ammonium. And so this is insoluble, so that's a solid. This is soluble, so that's aqueous. And so calcium carbonate, what does that consist of? It consists of calcium ions and carbonate ions in some kind of lattice. And then here we have hydrogen ions and pretty much sulfate ions. This. And so what we're going to do is we're going to look for other ion combinations. We have this ion combination, calcium with carbonate. We have this ion combination, hydrogen ions and sulfate ions. And so looking at other ion combinations, what we can do is we could try calcium ions with sulfate ions. If we do calcium ions with sulfate ions, which we form here, calcium sulfate. And then we can try hydrogen ions with carbonate ions. Hydrogen ions with carbonate likes to form what? Carbonic acid. Now we go over here, calcium sulfate. Sulfates are all soluble except for silver, mercury, lead, calcium. Calcium. Calcium's an exception. So most sulfates are soluble except calcium's not. And so this is going to result in what we call a precipitate. But I'm going to put a little asterisk there because of this. Calcium sulfate is also a solid. And so we have something called competing precipitates. Competing precipitates. And so when we look at these two precipitates, it depends on which of these two precipitates is more stable. You know, which way is the uphill direction? Which way is the downhill direction? What we want is we want to go downhill. That is, we want to go from higher energy to lower energy. And so is this precipitate more stable than that precipitate? We have to find out. And so what might give us clues? Well, charge. You know, the charge might give us clues. But the charges are the same because calcium's 2 plus, carbonate's 2 minus, sulfate is 2 minus. What else does the lattice depend on? It also depends on the size of the species, because this is Coulomb's law of electrostatic attraction. But you know, this is getting more complex. If I wanted to know which one's more stable, then maybe I should do this rather than trying to do it theoretically or that sort. Maybe I should try to do this via some experimental data. And so let's take a look at this. Calcium sulfate. If I look at calcium sulfate here, One of the things I can see for the experimental data is this. Take a look at that melting point. (2660 Fahrenheit, or 1460 C. 1460 C. Okay, then let's take a look at calcium carbonate. If I look at calcium carbonate, I see 1339 C for calcium carbonate. For calcium sulfate, 1460 C. So, based on melting point, which one do you think is more stable? Calcium sulfate. Why? Yeah, it has a higher melting point. Excuse me. So in order to melt it, we have to break apart the ions. So the higher the melting point, that must mean the ions are held together more strongly. And so we really didn't do it theoretically. We just did it based on some experimental data. So calcium sulfate 1460 versus calcium carbonate 1339. Not a huge difference. All right, then there's another thing we can look for too. The other thing that we could look for is solubility. We have two ways of thinking about solubility. One way is qualitative. So for example, sodium chloride, is it soluble or insoluble? Soluble. Group 1 salts are all soluble, so we call this soluble, or S. This is qualitative. So, is there a limit? You know it's soluble. Salt is soluble in water. Is there a limit to how much salt you can dissolve in water? Let's say I want the saltiest salt water I can make. Can I dissolve an infinite amount of salt in water? No. There is going to be a maximum. Let's say. Do you know what that maximum is? When I look at this quantitatively, well, you know what that maximum is. That's also called solubility. And so, if I want to figure out what the maximum is, I would look it up in a book or Wikipedia. In this case, I'll just look it up on Wikipedia. And I look up this number here. Solubility in water. If I look at this number here, solubility in water comes out to 360 grams per liter. That's the max I can dissolve. I can dissolve up to 360 grams per liter. And so let's say I had 370 grams. Could I get all to dissolve in the liter? No, I mean 10 grams would stay. That's solid. Or 36 grams per 100 milliliters. 36 grams per 100 milliliters. So if I try to get 37 grams of salt to dissolve in 100 milliliters, I wouldn't be able to do that. And so these are two. And so what solubility means is this. Solubility just means that if something's soluble, it just means that greater than 0.1 moles of molecules, formula units, will dissolve per liter of solution. Insoluble means that less than 0.1 moles will dissolve per liter. Sugar. Is it soluble or insoluble? Sugar. Sugar is soluble in water. Is it infinitely soluble? Can I make, let's say I want to make super sweet coffee. Could I dissolve, let's say, 100 sugar cubes in a cup of coffee? Probably not. There's going to be a limit. That limit, although I probably could dissolve more than 0.1 moles, so it's going to be soluble, but it doesn't tell me, the qualitative doesn't tell me that limit. The same thing, if something's insoluble, is it 100% insoluble? Not necessarily, because what happens is the water molecules can collide with the surface ions here, and some of the water molecules are moving fast, and they can knock off some ions. Well, which one is easier to knock off ions off of, calcium carbonate or calcium sulfate? And so even though both of these are insoluble, a little bit can dissolve. Now what is that little bit? Well, for calcium carbonate, that little bit is this. Soluble in water? No. 0.013 grams per liter. 0.013 grams per liter is 13 milligrams. So we could dissolve 13 milligrams of calcium carbonate per liter. 13 milligrams per liter. Not much, therefore we call it insoluble. How about calcium sulfate? That was 13 milligrams per liter. Calcium sulfate is 2.1 grams per liter. A liter I have to multiply by 10, so 2.1 grams. So calcium sulfate is quite a bit more soluble. And so we have some conflicting data. The conflicting data is this. One, the melting point says that calcium sulfate is more stable. It's a higher melting point. But two, the solubility data says that calcium sulfate has a weaker lattice because it's easier to dissolve. And so this one turns out to be competing precipitates is advanced. We must compare the two solids. And then we could figure out which side is down, which side's up. Is it downhill going forward or is it uphill going forward? And so it's inconclusive. When we have these competing precipitates, we have to look at additional data, including things like melting point, solubility, or theoretically, what makes a strong lattice or not. And so this is not easy. But all we need is one driving force. And so the precipitate might be inconclusive because we don't know, which one is a more stable precipitate. If you go forward, the precipitate's calcium sulfate. If you go backwards, so we're going from here over to there, then calcium carbonate would be the precipitate here. So which precipitates is more stable? Well, that might not always be an easy question to answer. But if we're just looking for a driving force, then we might look at the other driving forces. What are the other driving forces that we have? One is stronger acid, two, weaker acid. And so here, the stronger acid would be sulfuric, and then over here, the weaker acid is carbonic acid. And so this is what we term a driving force, or DF, We're going from a stronger acid, which is less stable, to a weaker acid, which is more stable. So it's downhill going forward. It's downhill because these is more stable. But is it? What do you know about carbonic acid? Is carbonic acid stable? No, because carbonic acid is going to decompose into H2O liquid and CO2 gas. So it still is, the driving force is going from stronger acid to weaker acid, and that's still viable even though we're forming CO2. In this case, CO2 is actually considered an acid, but not in our normal sense. Okay, so we could say the driving force is stronger acid to weaker acid, but there's also one more driving force. And all we need is one, so this is enough to get this reaction to go. What's the other driving force? Let's see. Well, it's not oxidation reduction, it's gas form. So this is also a driving force here. So two driving forces. The third one is a little bit inconclusive, but we don't need all three for a reaction to go. We just need one. And so for sure there are 2 out of 3 here that'll work. Let's see. Okay, why don't you do this one here? Actually, I made a mistake. What was my mistake? You see that? In the name. Okay. Is lead a fixed charge or variable charge? It's variable charge. So my mistake was I didn't indicate what the charge on lead is. So the charge on lead should be lead, Roman numeral 2, iodide. And hydrochloric acid. So give that one a try and see what you get.